Before the invention of the transistor, the most important piece of electronic equipment was the vacuum triode. All radios used them, early televisions used them, heck, even early computers had rooms full of these jacked up light bulbs. But how do they work, and how and why were they invented? This is a story of a smudge on a light bulb, an assistant with a good memory, and a con man working around a patent. Ready? Let's go.
Electricity, 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 electricity.
It all started in 1880 with the regular light bulb. Thomas Edison had noticed that when his light bulbs broke, they would often create black smudges on the inside of the bulb near the positive end of the filament. He had worked very hard to make good vacuums, so he was pretty sure that they were not created by any substance inside the bulb. Therefore, he deduced that they must be something coming off of the filament itself. He then added a plate to the bulb, with the hope that whatever was emanating from the filament would stick on the plate and possibly keep the filament from breaking in the first place. The plate turned out to be not much help. However, he noticed that if he added another battery between the filament and the plate, something strange happened. The current could flow if the plate was positive, but would not flow if the plate was negative. Edison patented it as a voltmeter, although he didn't really know what was going on or why anyone would want this expensive and ineffective voltmeter. What was going on? Well, it all has to do with the movement of negatively charged electrons. In the light bulb, when the filament got hot, the electrons could become free. When the filament broke, the electrons would fly towards the positive end and leave that black smudge. If, before the filament broke, you added an extra voltage between the filament and the plate, and the filament was negatively charged and the plate positive, the negatively charged electrons could easily jump off the filament and onto the positively charged plate and let the current flow. If, however, the plate was negatively charged, then the electrons would stay on the plate as it was cold and not concentrated on a thin filament. This was called the Edison effect. Although aside from patenting it, Edison wasn't much interested in it. However, Edison had a young English technical advisor named John Ambrose Fleming who was interested. Fleming was there to help Edison with alternating current, which Edison quickly decided to reject and sent Fleming back to England. Jump forward 24 years to October of 1904. By this time, Fleming had become a technical advisor to Guglielmo Marconi, helping him with sending wireless telegraph signals. Marconi's biggest problem in 1904 was in his receiver. Marconi used a tube with little filaments that would stick together or cohere when a radio wave went through it, and then would be tapped when the signal was complete. It was slow and awkward and inefficient. According to an engineer at the time, the coherer quote was publicized as wonderful, and it was wonderfully erratic and bad. It would not work when it should, and it worked overtime when it should not. The year before, in 1903, a Canadian named Reginald Fessenden had made an electrolytic detector that used a chemical reaction to rectify or filter out one direction of the current so that it could be heard on headphones. Fleming felt that the detector did not work well at high frequencies. Also, they didn't hold the patent. He was thinking about the problem when he had, according to him, a sudden, very happy thought. Why not try the lamps? He wrote Marconi, quote, "I found a method of rectifying electrical oscillations, that is, making the flow of electricity all in the same direction." By November, Fleming filed for a patent for what was called a Fleming valve, or a vacuum diode, di for two, ode for path. Note that the Fleming valve was exactly the same as the Edison effect valve. What was different was how he used it. So let's talk a little bit about what Fleming did. Fleming used an antenna with a coil to receive the radio signal. He then had another coil so that the alternating current in the first coil would induce an alternating current in the second coil. He then had that signal go through a sensitive current meter called a mirror galvanometer and had one end of the signal go to the plate and one to the filament of his valve, heated by a battery. The valve thus made the signal one way so that the meter turned in one direction and could be recorded. Fleming did not use headphones, possibly because he was partially deaf. This worked pretty well, but it was not very popular, as it was expensive, and most people started using semiconductors in what were called crystal sets as rectifiers instead. However, one person was very interested in the Fleming valve, and his name was Lee de Forest. At the time, Lee de Forest was being sued by Reginald Fessenden for copying his electrolytic detector, so de Forest was on the hunt for a new detector. We know de Forest had read about the Fleming valve because in December of 1905, de Forest filed for a patent that used what he describes as, quote, an electric valve which has been fully described by J.A. Fleming. Then 5 weeks later, de Forest files for a patent for a new detector that is strikingly similar to the Fleming valve. They both had a filament and a plate in a vacuum tube and heated the filament with a battery. They also both took a radio wave from an antenna and passed it through the valve between the plate and the filament. In fact, there are only 4 very minor differences. First, de Forest used headphones instead of a current meter. Second, he added an extra battery. That didn't seem to do much. Third, he didn't use parallel coils, at least in this circuit. And fourth, he incorrectly thought that trace amounts of gas in the bulb were ionized, and that was what was causing the current to flow. So he insisted that the bulb not be a perfect vacuum. Because this device was used to make sound, and he incorrectly thought it had to do with the ionization of gas, he dubbed this an audion. Not surprisingly, Fleming sued. Meanwhile, de Forest started adding pieces of metal all over the place. He wrapped his valve in tinfoil. He circled the outside of it with wire. He had multiple connected plates inside the bulb. Then on Christmas Day of 1906, de Forest ordered a bulb with 3 connections: the filament, the plate, and between them a wire that was bent into a zigzag shape that he called a grid. Adding the 3rd wire in the middle was described in 1922 as, quote, the most important single step taken in the whole development of radio communication. So what did the wire do? Well, imagine you set up a vacuum triode by heating the filament with a battery and attaching a separate voltage so that the filament is negative and the plate is positive. In this case, the electrons would jump off the heated filament, past the grid wire, and onto the plate. Now imagine adding a weak signal to the grid wire. If you add a signal where the grid wire has a positive charge on it, many more electrons would be attracted to the grid and jump off the filament and onto the plate. This would vastly increase the current on the plate. If you add a signal to the grid wire with a negative charge, however, it would block the negative electrons from jumping onto the plate, cutting off the current. In this way, small changes in the grid wire can make big changes in the current coming out of the plate. This was both an electric amplifier and an electric rectifier, or one-way valve. Unfortunately, Lee de Forest couldn't get his device to work that well, and he mostly just used it as a complicated rectifier. In addition, de Forest was convinced that you needed a little bit of gas to make them work, possibly to distinguish it from the Fleming valve, which led to some low-quality triodes. Because the audion was expensive and complicated and had variable quality, very few people used it. It wasn't until 5 years after its invention, when a tenacious undergraduate named Howard Armstrong figured out how to make the triode sing by feeding the signal back to it in a system he called regeneration. This is what made the vacuum triode the Swiss Army knife for the next 50 years, meaning they used it for everything.
Sir, if it weren't for these babies, there wouldn't be any radio. Yes, and a million others owe their jobs to the vacuum tube, including myself. As a matter of fact, practically everybody has been benefited by it in some way.
And that story starts next time on The Secret History of Electricity.
Electricity, 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 electricity.
Thanks for watching my video. Please remember to give it a thumbs up, and if you haven't yet, subscribe. It's always a fun thing to do. If you're interested in learning more about Fessenden and how he made his electrolytic detector and the first AM signals, I have a video about that. If you're interested in learning more about Lee de Forest and his colorful life, I have a video about that. And make sure you check out the next one about regeneration and positive feedback and Howard Armstrong. It's going to be a good one. Okay, have a good day.